What if the most groundbreaking discovery in human history has already happened? Not in some distant galaxy, but right here in our own solar system, with two mysterious visitors that arrived precisely when our technology was advanced enough to detect them, moving on trajectories so mathematically improbable that the odds of natural occurrence hover at just 0.005%, suggesting perhaps that someone or something wanted us to notice. Tonight, as I watched the latest images from the Hubble Space Telescope capturing 3/Atlas racing through our cosmic neighbourhood at over 130,000 miles per hour, I felt that familiar tingle of wonder that makes this work in science for sleep so deeply satisfying. Knowing that somewhere out there, a sleepy scientist just like you is about to fall asleep fast to the most extraordinary story our species has ever encountered. Good evening, beautiful dreamers, and welcome to another journey through the infinite mysteries that surround our little blue world. I am your devoted guide through the cosmos, here to transform the most mind-bending discoveries of our time into the gentle lullabies that will carry you into the most peaceful rest. Before we embark on tonight's adventure through interstellar space, and the visitors that may have changed everything we thought we knew about our place in the universe, I must warn you that this particular story might just be too fascinating for sleep. We will be exploring evidence so compelling, so perfectly strange, that you might find yourself wide awake with cosmic wonder. But first, if these nightly expeditions through the mysteries of science bring you the comfort and curiosity that fills my heart each time I share them, it would mean the universe to me if you could offer a gentle like and perhaps subscribe to join our ever-growing family of cosmic dreamers. There is also something wonderfully new called the hype function that YouTube has gifted us, and if you see that magical button below this video, pressing it is honestly one of the most beautiful ways to help our community of curious souls discover these stories together. And please, do tell me in the comments where in this marvellous world you are listening tonight, what time it is in your corner of our planet, and if you feel like sharing the most wonderfully strange dream you have ever experienced. I read every single comment with such joy and do my very best to reply to each one, because in this vast cosmos we are all connected by our shared sense of wonder. Picture, if you will, millions of us scattered across this turning world, from Tokyo to London, from small villages nestled in mountain valleys to bustling cities that never sleep. All of us looking up at the same stars, all of us carried along on the same cosmic journey, all of us about to discover together why two ancient wanderers from the depths of space might just be the most important visitors our world has ever received. Now, settle back into your most comfortable position, let your breathing slow and deepen, and prepare to embark on a story that begins not with rockets or telescopes, but with two objects so mysterious, so perfectly anomalous, that they have forced some of our most brilliant scientists to ask a question that once belonged only to science fiction. Are we alone? Or have we already been found? The first cosmic visitor arrived on October 19, 2017, when astronomers at the Pan-STARRS 1 telescope in Hawaii noticed something that should not have existed. Moving through our solar system at nearly 200,000 miles per hour was an object unlike anything they had ever seen, tumbling end over end on a trajectory that screamed of foreign origins. This was not one of our familiar comets with their glorious tails of ice and dust, nor was it one of the countless asteroids that have called our solar system home for billions of years. This visitor, which the Hawaiian astronomers named Oumuamua, meaning scout or messenger from afar arriving first, was something entirely different. Think about that name for a moment, messenger from afar arriving first, as if the universe itself was whispering to us that this would not be the last such visitor, that perhaps it was exactly what its name suggested, a scout sent ahead to prepare the way for something more. The shape of Oumuamua defied every expectation. Where asteroids are typically rounded or irregularly lumpy, and comets display the soft, fuzzy characteristics of their icy composition, Oumuamua appeared to be elongated in the most extreme way, stretched like a cosmic cigar, or perhaps flattened like an enormous cosmic pancake. The exact shape remained maddeningly unclear because even our most powerful telescopes could only capture it as a point of light. But the way that light brightened and dimmed as the object rotated told a story of something 10 times longer than it was wide. No natural object in our solar system has ever displayed such an extreme ratio. The most elongated asteroids we've ever observed are at most 3 times longer than they are wide, making Oumuamua not just unusual, but physically unprecedented in our experience of how cosmic objects form and evolve. But the shape was only the beginning of the mystery. As Oumuamua swung around our sun and began its journey back toward the stars, something extraordinary happened that sent ripples of confusion through the astronomical community. The object began to accelerate, not in the way that gravity would predict, but as if something was pushing it forward, giving it an extra boost that could not be explained by the gravitational forces of our solar system. This was not the gentle acceleration that comets sometimes display when heated gases escape from their surfaces, creating a natural rocket effect. Oumuamua showed no signs of such outgassing, no tail, no coma of particles, nothing that would suggest it was venting material into space. Yet it was speeding up in a way that broke our understanding of how objects move through the cosmos. Harvard astronomer Avi Loeb, a man who has spent his career studying the most exotic phenomena in the universe, from black holes to the earliest moments after the Big Bang, looked at this evidence and reached a conclusion that sent shockwaves through the scientific world. In a paper published in the prestigious astrophysical journal Letters, Loeb and his colleagues suggested that the most plausible explanation for Oumuamua's behaviour was that it was not a natural object at all, but rather a piece of technology, perhaps a light sail powered by the pressure of starlight itself, possibly a derelict from some long-expired galactic civilization. The response from the scientific community was swift and almost universally negative. Colleagues dismissed Loeb's ideas as sensationalistic, career-damaging and scientifically irresponsible. The pressure to find natural explanations intensified, leading to increasingly creative theories about hydrogen icebergs, nitrogen fragments from Pluto-like worlds, and exotic materials that might behave in unexpected ways when heated by our sun. Yet none of these alternative explanations could fully account for all of Oumuamua's strange properties. The hydrogen theory required the complete evaporation of the object's hydrogen content, something that seemed physically impossible given the observed timeline. The nitrogen theory struggled with the extreme shape and reflective properties. Each natural explanation solved some aspects of the mystery while creating new problems in others. As Oumuamua faded into the darkness of interstellar space, leaving behind more questions than answers, the scientific community was left with an uncomfortable truth. For the first time in the history of astronomy, we had encountered an object that truly defied easy categorization, something that forced us to expand our definitions of what was possible in the cosmos. But Oumuamua was not destined to remain alone in its mysterious category. On August 30th, 2019, amateur astronomer Gennady Borisov spotted another interstellar visitor approaching our solar system. This second object, designated 2E/Borisov, was everything that Oumuamua was not. It displayed all the characteristics of a traditional comet, complete with a beautiful tail and coma that confirmed its icy composition. 2I/Borisov was so perfectly normal in its behaviour that it almost seemed to be making a point, as if the universe was saying, "See, this is what a natural interstellar object looks like." The presence of 2I/Borisov provided crucial context for understanding Oumuamua. If interstellar objects were common, and if they typically behaved like normal comets, then Oumuamua's anomalous properties became even more significant. Here was clear evidence that not all visitors from beyond our solar system were created equal, that some might indeed be fundamentally different from others. For nearly 6 years, astronomers waited and watched, knowing that the next interstellar visitor might provide the key to understanding what Oumuamua truly was. Survey telescopes scanned the skies with increasing sophistication, automated systems designed to catch the faintest traces of objects moving on hyperbolic trajectories that would mark them as foreigners to our solar system. Then, on July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System, known as ATLAS, detected something extraordinary. Racing toward our inner solar system at over 137,000 miles per hour was another interstellar object, designated 3/Atlas, that would soon prove to be even more mysterious than its predecessors. 3I/Atlas was different from the moment of its discovery. Where Oumuamua had been spotted as it was already leaving our solar system, providing only a brief window for observation, 3I/Atlas was caught early in its approach, offering unprecedented opportunities for detailed study. Where 2I/Borisov had followed a relatively straightforward trajectory that brought it close to the Sun before heading back out, 3I/Atlas was following a path so precisely calculated that it seemed almost intentional. The trajectory of 3I/Atlas is perhaps its most startling feature. The object is moving within 5 degrees of the ecliptic plane, the narrow band of space where all the planets orbit our Sun. For a random interstellar object to hit this narrow target, the odds are less than 0.2%, but 3I/Atlas was not just passing through this plane, it was following a path that would bring it remarkably close to 3 major planets, Jupiter, Mars, and Venus. The combined probability of such close approaches to multiple planets by pure chance is so low that Avi Loeb calculated it at just 0.005%. To put this in perspective, you're more likely to win the lottery multiple times than for a random interstellar object to naturally follow the precise trajectory that 3I/Atlas is following. But the mathematical improbabilities were only the beginning. As astronomers studied 3I/Atlas more closely, they discovered that it was displaying characteristics that echoed Oumuamua's mysterious behavior while adding new anomalies of its own. The object appeared to be significantly larger than its predecessors, with estimates ranging from several kilometers to over 20 kilometers in diameter, making it potentially the largest interstellar object ever detected. Early observations suggested that 3I/Atlas was showing signs of cometary activity, with a faint coma of particles surrounding its nucleus. This should have been reassuring, evidence that it was behaving like a normal comet as it heated up in the warmth of our Sun. But as the observations continued, strange inconsistencies began to emerge. The brightness and behavior of 3I/Atlas did not match what astronomers expected from a natural comet of its size and composition. The object appeared to be more reflective than typical comets, suggesting a surface composition that was unusual or perhaps artificially enhanced. Most puzzling of all, the rate at which it was brightening as it approached the Sun did not follow the standard patterns that govern how comets behave when heated. Avi Loeb, already famous for his controversial theories about Oumuamua, looked at the mounting evidence surrounding 3I/Atlas and reached an even more startling conclusion. In a paper co-authored with Adam Hibbard and Adam Crowell from the Initiative for Interstellar Studies, Loeb proposed that 3I/Atlas might not be a natural object at all, but rather a piece of potentially hostile alien technology, possibly a reconnaissance probe sent by an advanced civilization to study our solar system and evaluate our planet. The paper, while clearly labelled as a pedagogical exercise and thought experiment, laid out a compelling case for why 3I/Atlas might represent evidence for what science fiction writer Liu Cixin called the dark forest hypothesis. This theory suggests that the reason we have not detected signs of alien civilizations is not because they do not exist, but because they remain silent to avoid detection by potential predators or competitors. In this scenario, the universe is like a dark forest filled with hunters, where revealing your presence might result in your destruction. Civilizations that survive are those that remain hidden, moving through the cosmos like shadows, gathering intelligence while avoiding detection. If this hypothesis is correct, then objects like Oumuamua and 3I/Atlas might represent exactly the kind of covert reconnaissance missions that an advanced civilization would send to study potential targets or threats. The timing of these visits is particularly intriguing. Both objects arrived during a narrow window in human history when our technology was advanced enough to detect them, but not advanced enough to intercept them for detailed study. Oumuamua was spotted only as it was leaving our solar system, providing just weeks for observation before it faded beyond the reach of our telescopes. 3I/Atlas is following a trajectory that makes it extremely difficult to reach with current spacecraft technology, almost as if it was designed to remain just beyond our grasp. Even more suspicious is the fact that 3I/Atlas will reach its closest approach to the Sun in late October, when it will be positioned on the opposite side of our star from Earth, hidden from detailed observation by our planet's most powerful telescopes. Loeb suggests that this timing could be intentional, designed to prevent us from getting clear images of the object when it is brightest and potentially most revealing of its true nature. the scientific community's response to these theories has been predictably skeptical. Leading astronomers have dismissed Loeb's ideas as sensationalistic and unscientific, arguing that the available evidence points clearly toward natural explanations. They point out that 3I/Atlas is displaying obvious signs of cometary activity, including the formation of a coma and the beginnings of a tail as it approaches the Sun. Dr. Richard Moisel, head of planetary defense at the European Space Agency, stated flatly that there have been no signs pointing to non-natural origins of 3Y/Atlas in the available observations. Other researchers have noted that while the object's trajectory is indeed unusual, it falls within the range of possibilities for a natural interstellar comet, especially one that has been travelling through space for millions or billions of years. Yet even the skeptics acknowledge that 3I/Atlas presents puzzles that are not easily resolved. The object's size, brightness, and trajectory all push the boundaries of what we expect from natural interstellar objects. Its approach angle, coming side-on to the Sun's motion through the galaxy rather than head-on like its predecessors, suggests a different origin or perhaps a different purpose. As 3I/Atlas continues its journey through our solar system, racing toward its October encounter with the Sun, astronomers around the world are mobilizing every available telescope to study it in unprecedented detail. The Hubble Space Telescope has already captured the clearest images yet of the object, revealing its teardrop-shaped coma and providing better estimates of its size and composition. The James Webb Space Telescope, humanity's most powerful instrument for studying the cosmos, has turned its infrared gaze toward 3W/Atlas, analyzing the chemical composition of its coma and searching for any signatures that might reveal its true nature. Ground-based observatories from Chile to Hawaii are tracking its progress, measuring its brightness, rotation, and any changes in its behavior as it heats up in the increasing warmth of our Sun. Each new observation adds pieces to a puzzle that grows more complex rather than simpler. Early spectroscopic analysis has revealed that 3I/Atlas contains significant amounts of water ice, carbon dioxide, and other materials typical of comets, but the proportions of these materials and the way they are behaving as the object heats up do not match perfectly with theoretical models of how interstellar comets should evolve. The object's rotation is also puzzling. Unlike typical comets, which often tumble chaotically as they approach the Sun, 3I/Atlas appears to be rotating in a remarkably stable manner, almost as if it has been designed to maintain a specific orientation relative to the Sun and planets. This stability could be natural, the result of millions of years of evolution in interstellar space, but it could also suggest some form of attitude control or artificial stabilization. Perhaps most intriguingly, 3I/Atlas appears to be releasing materials at a rate that is inconsistent with its observed brightness and coma formation. Typical comets follow well-understood relationships between their distance from the Sun, their rate of material loss, and their visible brightness. 3I/Atlas seems to be breaking these rules, suggesting either that its composition is highly unusual or that some other process is governing its behavior. Avi Loeb has proposed several tests that could potentially distinguish between natural and artificial origins for 3I/Atlas. As the object passes close to Mars in early October, he suggests using the high-resolution imaging camera aboard NASA's Mars Reconnaissance Orbiter to look for any smaller objects or probes that might be deployed from the main body. If 3I/Atlas were to release such objects, it would be strong evidence for artificial origins. He also proposes using the Juno spacecraft, currently orbiting Jupiter, to study 3Y/Atlas when it passes within 53.6 million kilometers of the giant planet in March 2026. Such close-range observations could reveal details about the object's structure, composition, and behavior that are impossible to obtain from Earth-based telescopes. The European Space Agency's upcoming Comet Interceptor mission, scheduled to launch in 2028, represents humanity's best hope for getting a close-up look at future interstellar visitors. This mission is designed to wait in space until a suitable target appears, then rapidly maneuver to intercept it for detailed study. While 3I/Atlas will likely be beyond reach by the time Comet Interceptor is operational, the mission could provide crucial data about the next interstellar visitor to enter our solar system. The implications of the 3I/Atlas mystery extend far beyond astronomy. If the object were confirmed to be of artificial origin, it would represent the first concrete evidence that advanced alien civilizations exist and that they are actively studying our solar system. Such a discovery would fundamentally transform our understanding of our place in the universe and raise urgent questions about the intentions of our cosmic visitors. The dark forest hypothesis that Loeb invokes suggests that such visitors might not be benign explorers, but rather scouts for civilizations that view other technological species as potential threats to be eliminated. If this interpretation is correct, then the appearance of objects like Oumuamua and 3Y/Atlas might signal that humanity has reached a level of technological development that has attracted unwanted attention from hostile neighbours. This possibility has led some researchers to call for increased vigilance and even defensive preparations. If alien civilizations are indeed surveying our solar system, then our radio transmissions, space activities, and technological signatures have likely already revealed our presence. The question becomes not whether we have been detected, but whether we are being evaluated for peaceful contact or potential elimination. Of course, the vast majority of scientists believe that such scenarios remain firmly in the realm of science fiction. They argue that the evidence for artificial origins remains weak, and that natural explanations, while complex, are far more likely to be correct. They point out that the universe is full of strange objects and phenomena that initially defy explanation, but ultimately yield to scientific understanding. The history of astronomy is filled with mysterious objects that were initially misunderstood. Pulsars were once thought to be possible alien beacons before being recognized as rapidly rotating neutron stars. Gamma-ray bursts were initially so puzzling that some scientists speculated they might be evidence of alien warfare before being identified as the deaths of massive stars. Fast radio bursts continue to puzzle astronomers today, though natural explanations are considered far more likely than artificial ones. Yet Oumuamua and 3I/Atlas present challenges that go beyond typical astronomical puzzles. Their behaviour is not just unusual, but appears to violate fundamental principles about how natural objects should behave in interstellar space. The mathematical improbabilities surrounding their trajectories strain credibility, especially when combined with their other anomalous properties. The debate over these objects reflects deeper questions about how science should approach genuinely unprecedented phenomena. Traditional scientific methodology favours the simplest explanations and requires extraordinary evidence for extraordinary claims. But what happens when the simplest explanations fail to account for the observed evidence, and when the extraordinary claims begin to accumulate supporting data? Avi Loeb argues that science has become too conservative, too willing to dismiss possibilities that challenge conventional thinking. He points out that many of the greatest discoveries in the history of science were initially ridiculed by the establishment, from Galileo's support for heliocentrism to Wegener's theory of continental drift. He suggests that the search for extraterrestrial intelligence should be treated as a legitimate scientific endeavour, with the same rigour and openness to evidence that characterises other fields of research. Critics respond that Loeb's approach abandons the careful scepticism that protects science from wild speculation and premature conclusions. They argue that extraordinary claims do indeed require extraordinary evidence, and that the evidence for artificial origins of interstellar objects remains far from extraordinary. They worry that sensationalistic theories about alien visitors distract from the real scientific value of studying these objects and undermine public understanding of how science actually works. This tension between openness to radical possibilities and adherence to rigorous standards reflects one of the fundamental challenges facing science in the 21st century. As our technology becomes more sophisticated and our observations more precise, we are likely to encounter phenomena that push the boundaries of our understanding. How we respond to such challenges will determine whether science continues to evolve and grow or becomes trapped by its own conservative instincts. The story of 3I/Atlas is still unfolding as the object races toward its closest approach to the Sun. Over the coming months, astronomers will gather unprecedented amounts of data about its composition, structure, and behaviour. This information will either support natural explanations for its anomalous properties or add to the mounting evidence that something extraordinary is visiting our solar system. Regardless of the ultimate conclusion about 3I/Atlas, its discovery has already transformed our understanding of interstellar objects and their significance for astrobiology. The fact that we have now detected 3 such objects in less than a decade suggests that they are far more common than previously thought. Some estimates suggest that dozens or even hundreds of interstellar objects may be passing through our solar system at any given time, most too small or too distant to detect with current technology. This realization has profound implications for the search for life beyond Earth. If interstellar objects are common, then they represent a previously unrecognized mechanism for transporting materials, and possibly even life itself, between star systems. The process of panspermia, in which life spreads throughout the galaxy via natural mechanisms, becomes much more plausible if there is a constant stream of objects carrying materials from one stellar system to another. Even if 3I/Atlas and Oumuamua prove to be entirely natural, their study is revolutionizing our understanding of planetary formation and evolution throughout the galaxy. These objects carry with them chemical signatures and physical properties that reflect the conditions around their parent stars, providing unique insights into how planetary systems form and evolve in environments very different from our own. The discovery of interstellar objects also highlights the rapid advancement of astronomical survey technology. Projects like ATLAS, LINEA, and the upcoming Vera Rubin Observatory are dramatically increasing our ability to detect small, fast-moving objects throughout the solar system. As these systems become more sensitive and comprehensive, they are likely to detect many more interstellar visitors, providing a growing database for understanding these mysterious objects. Some researchers estimate that the Vera Rubin Observatory, when it becomes fully operational, could detect dozens of interstellar objects each year. This wealth of data will allow for statistical studies that could reveal patterns in their origins, compositions, and trajectories. If any of these objects prove to be artificial, such patterns might reveal the locations of their parent civilizations or the purposes of their missions. The search for artificial objects in space is becoming increasingly sophisticated, with researchers developing new techniques for distinguishing between natural and technological signatures. These methods include looking for unusual material compositions, non-gravitational accelerations, geometric shapes that are unlikely to occur naturally, and emission of artificial signals or radiation. Project Galileo, established by Avi Loeb in 2021, represents the most systematic effort to search for evidence of extraterrestrial technology in our vicinity. The project uses advanced instruments to monitor the skies for anomalous objects and phenomena, including potential technological artifacts left behind by visiting civilizations. While the project has yet to announce any definitive discoveries, it represents a new approach to SETI that focuses on physical evidence rather than radio signals. The possibility that we are being visited by alien technology also raises important questions about how humanity should respond to such contact. Traditional SETI protocols assume that first contact will occur through radio communication, allowing for careful consideration of how to respond. But physical visitation presents immediate challenges that may not allow for extended deliberation. If objects like 3I/Atlas are indeed artificial, then we are already in a form of contact with alien intelligence, even if it is one-sided. The question becomes whether we should attempt to communicate with such visitors, ignore them, or take defensive measures against potential threats. Different schools of thought argue for each approach, reflecting deep uncertainties about alien intentions and capabilities. Some researchers argue for attempting active communication with suspicious interstellar objects, using powerful radio transmitters to send signals toward them in hopes of eliciting a response. Others warn that such attempts could be dangerous, potentially revealing our location and capabilities to civilizations that might have hostile intentions. The development of planetary defense capabilities takes on new urgency if interstellar objects might include artificial threats. Current efforts focus primarily on detecting and deflecting natural asteroids and comets that might impact Earth, but defending against technological threats would require entirely different approaches, potentially including the development of new detection systems, interception capabilities, and even offensive weapons. International cooperation becomes crucial in addressing these challenges, as no single nation has the resources or authority to represent all of humanity in potential contact scenarios. Organisations like the United Nations Office for Outer Space Affairs are beginning to develop frameworks for coordinating global responses to extraterrestrial contact, but much work remains to be done. The implications extend beyond immediate defence concerns to fundamental questions about human unity and identity. The confirmation that we are not alone in the universe would likely trigger profound philosophical, religious, and cultural transformations. Different societies might react very differently to such news, potentially leading to conflict or fragmentation at precisely the moment when human unity becomes most important. Educational systems around the world would need to rapidly adapt to incorporate new understandings about our place in the cosmos. Scientific literacy becomes not just an academic concern but a matter of planetary security, as citizens need to understand the evidence and implications of potential contact scenarios. The economic implications could be equally transformative, as confirmation of advanced alien technology might trigger massive investments in space technology, defense systems, and scientific research. The knowledge that other civilizations have achieved interstellar travel could accelerate human efforts to develop similar capabilities, potentially leading to rapid advances in propulsion, materials science, and space exploration. Yet, for all the speculation about alien visitors and their implications, the most likely scenario remains that 3I/Atlas and Oumuamua are natural objects whose anomalous properties reflect processes and materials that we do not yet fully understand. The universe is vast and ancient, filled with phenomena that exceed our current knowledge and imagination. Even natural interstellar objects represent profound scientific opportunities, offering insights into the formation and evolution of planetary systems throughout the galaxy. They carry with them samples of materials from stellar environments that we may never be able to visit directly, providing laboratory specimens from alien worlds that have travelled for millions or billions of years to reach us. The study of these objects is pushing the boundaries of multiple scientific disciplines, from astronomy and planetary science to astrobiology and materials research. New techniques for analysing their compositions, structures, and behaviours are advancing our capabilities for studying all manner of small solar system bodies, with applications ranging from asteroid mining to planetary defence. The technological challenges of intercepting fast-moving interstellar objects are driving innovations in spacecraft design, propulsion systems, and mission planning. Concepts like solar sails, ion drives, and gravitational assists are being refined and combined in new ways to enable rapid response missions to these fleeting visitors. Perhaps most importantly, the discovery of interstellar objects has transformed our perspective on the solar system, from a closed, isolated environment to an open system that regularly exchanges materials with the broader galaxy. We now know that we live in a cosmic environment that is constantly being visited by messengers from distant worlds, carrying news of stellar systems and planetary processes far beyond our current reach. This realization connects us to the universe in ways that previous generations could barely imagine. We are not isolated inhabitants of a single star system, but participants in a galactic community of worlds and processes that span hundreds of billions of years and countless stellar environments. Whether or not any of our visitors are artificial, they remind us that we are part of something immeasurably larger than ourselves. As 3I/Atlas continues its journey through our solar system, accelerating toward its October encounter with the Sun, it carries with it the hopes and fears of a species that is just beginning to understand its place in the cosmos. Whether it proves to be an ancient comet, a fragment of an alien world, or something even more extraordinary, it has already changed forever how we think about our cosmic neighbourhood and our own future among the stars. The coming months will bring unprecedented observations as humanity's most advanced instruments focus their attention on this mysterious visitor. Each new piece of data will add to our understanding, gradually revealing whether we are witnessing a natural phenomenon of extraordinary complexity or the first confirmed visit from an alien civilization. In either case, we are living through a moment of profound discovery, a time when the boundaries between science and speculation, between the known and the unknowable, are being redrawn by objects that have travelled across the vast emptiness between stars to visit our small corner of the galaxy. The age of interstellar archaeology has begun, and we are its first practitioners, tasked with interpreting messages written in trajectories and compositions by processes and perhaps intelligences that we're only beginning to comprehend. As you drift towards sleep tonight, carried along by our planet's rotation through the cosmic dance that connects us to every star in the sky, remember that somewhere high above, racing through the darkness at speeds that dwarf our fastest spacecraft, ancient visitors continue their journeys between worlds, bearing witness to our existence and perhaps reporting back to civilizations whose names and natures we can only begin to imagine. The universe has sent us messengers, whether natural or artificial, and we are finally advanced enough to receive their communications. What they tell us about our cosmos, our origins, and our future remains to be discovered, but one thing is certain: we are no longer alone in thinking we might not be alone. The evidence has arrived, travelling across the emptiness between stars to find us here, in this moment, in this place, ready at last to join the conversation that may have been going on around us for longer than we ever dared to dream. The mathematics of cosmic encounters tell stories that sometimes strain our ability to believe in coincidence. When we calculate the probability that 3 I/Atlas would arrive at precisely the moment when humanity possesses the technology to detect it but not yet the capability to intercept it, when we consider that its trajectory brings it close to 3 major planets in our solar system, with odds of less than 1 in 20,000, when we examine the fact that both it and Oumuamua appeared during the brief window when our civilization first developed the ability to distinguish interstellar objects from local residents, we begin to see patterns that suggest something far more intentional than random cosmic wandering. Dr. Avi Loeb has developed what he calls the Loeb scale for interstellar objects, a rating system from 0 to 10 where 0 represents a definitely natural object and 10 indicates definitely technological origins. Currently he assigns 3 I/Atlas a rating of 6 on this scale, acknowledging that while artificial origins remain speculative, the accumulating evidence makes purely natural explanations increasingly strained. The scale itself represents a fascinating attempt to quantify the unquantifiable, to apply scientific rigor to questions that blur the boundaries between astronomy and astrobiology. At level 0, we find objects like Tui/Borisov, which displayed all the expected characteristics of a natural interstellar comet. At level 10 would be objects that emit artificial signals, perform obvious maneuvers, or deploy smaller craft. 3 I/Atlas, with its mathematically improbable trajectory and anomalous physical properties, occupies an uncomfortable middle ground, where natural and artificial explanations compete for credibility. But the Loeb scale represents more than just an academic exercise in classification. It reflects a growing recognition within the scientific community that we need new frameworks for evaluating potential evidence of extraterrestrial intelligence. Traditional SETI has focused on radio signals and optical communications, assuming that alien civilizations would announce their presence through intentional broadcasts. But what if advanced civilizations prefer more subtle approaches, using physical reconnaissance rather than electromagnetic advertisement? The concept of silent surveillance makes evolutionary sense from the perspective of cosmic sociology. In a universe where resources are limited and competition between civilizations might be fierce, revealing your location and capabilities could be tantamount to painting a target on your world. Far safer to remain hidden while gathering intelligence about potential neighbors, assessing their technological development and possible threat levels before deciding whether to make contact or maintain distance. This hypothesis gains credibility when we consider the extreme age and size of our galaxy. The Milky Way has been forming stars and potentially habitable worlds for over 13 billion years, providing ample time for multiple civilizations to arise, evolve, and spread throughout the galactic disk. If even a small fraction of these civilizations survived long enough to develop interstellar capabilities, the galaxy should be teeming with advanced life forms. Yet we observe what appears to be cosmic silence, a phenomenon so puzzling that it has its own name, the Fermi paradox. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" During a 1950 lunch discussion about the statistical likelihood of alien life, the paradox highlights the apparent contradiction between the high probability of extraterrestrial civilizations and the complete absence of evidence for their existence. Numerous solutions to the Fermi paradox have been proposed over the decades. Perhaps life is far rarer than we assume, requiring such specific conditions that Earth represents a cosmic anomaly. Perhaps intelligence is even rarer, with most life forms never evolving beyond simple organisms. Perhaps technological civilizations inevitably destroy themselves before achieving interstellar capabilities, victims of their own success in developing powerful technologies. But the dark forest hypothesis offers a more chilling explanation. Perhaps advanced civilizations do exist throughout the galaxy, but they remain hidden because the universe is a dangerous place where revealing your presence attracts the attention of hostile neighbors. In this scenario, any civilization that broadcasts its location or capabilities risks being eliminated by more advanced competitors who view all potential rivals as existential threats. Liu Cixin, the Chinese science fiction author who popularized the dark forest concept in his award-winning novel of the same name, drew inspiration from game theory and evolutionary biology to construct a universe where cooperation between civilizations is impossible because trust cannot be established across the vast distances and timescales of interstellar space. In such an environment, the safest strategy is to remain silent while actively searching for and potentially eliminating any other civilizations you discover. If the dark forest hypothesis is correct, then objects like Oumuamua and 3Y/Atlas might represent exactly the kind of covert reconnaissance missions that advanced civilizations would deploy to study potential targets. Their anomalous properties could reflect technologies designed to appear natural while gathering detailed intelligence about our solar system, our planet, and our rapidly developing technological capabilities. The timing of these visits becomes particularly significant in this context. Both objects arrived during a narrow window in human history when our electromagnetic emissions first became detectable from interstellar distances. Our radio and television broadcasts, radar installations, and satellite communications have been radiating into space for less than a century, but they represent clear signatures of a technological civilization that has recently emerged from its home planet. From the perspective of galactic surveillance, Earth would have transitioned from an apparently lifeless world to an obvious technological civilization within the span of just a few decades. Such a rapid transformation would likely trigger immediate interest from any monitoring systems designed to detect emerging civilizations throughout the galaxy. The response time for such surveillance missions depends on how advanced the monitoring civilization might be and how far away they are located. If they possess technology that allows faster-than-light travel or communication, they could respond to our electromagnetic signatures almost immediately. If they are limited to subliminal velocities like us, but possess highly advanced propulsion systems, they might still be able to deploy reconnaissance probes within decades of detecting our emergence. Alternatively, the galaxy might already be seeded with dormant monitoring systems, ancient artifacts left behind by long-vanished civilizations to watch for signs of emerging intelligence. Such systems could have been waiting in our outer solar system for millions or billions of years, activating only when triggered by clear evidence of technological development on Earth. This possibility gained support from theoretical studies of optimal strategies for galactic exploration and surveillance. Rather than attempting to visit every potentially habitable world directly, an advanced civilization could achieve far greater coverage by deploying self-replicating probes that establish monitoring stations throughout the galaxy. These probes could remain dormant for vast periods of time, using minimal energy while watching for signs of emerging civilizations. When such signs appear, the probes could activate and begin detailed reconnaissance missions, gathering intelligence about the new civilization's technological capabilities, social structures, and potential threat levels. Depending on what they discover, they might recommend peaceful contact, continued monitoring, or preemptive elimination of the emerging threat. The behavior patterns exhibited by Oumuamua and 3I/Atlas could be consistent with such reconnaissance missions. Both objects followed trajectories that provided excellent opportunities to study our solar system and our planet, while remaining difficult for us to intercept or examine closely. Both displayed anomalous properties that could reflect advanced technologies disguised as natural phenomena. Consider the strategic advantages of 3Y/Atlas's trajectory. Its path will take it close enough to Jupiter to study the giant planet's moons, some of which might be suitable for establishing monitoring stations or resource extraction operations. Its approach to Mars occurs at a time when multiple human spacecraft are operating in the Martian system. providing opportunities to observe our technological capabilities up close. Most intriguingly, 3I/Atlas will be hidden behind the Sun during its closest approach to our star, positioned precisely where Earth-based telescopes cannot observe it clearly. This timing could be coincidental, but it could also represent deliberate planning to avoid detailed examination during the most revealing phase of its mission. The possibility that 3I/Atlas might deploy smaller probes or instruments during this hidden phase adds another layer of concern to the reconnaissance scenario. If the object were to release microsatellites or landing probes while shielded from our observation, we might never know that such deployment had occurred. These smaller artifacts could remain in our solar system long after the main object departs, continuing their surveillance mission indefinitely. Avi Loeb has proposed specific tests that could potentially detect such deployment activities. High-resolution imaging from spacecraft like the Mars Reconnaissance Orbiter could search for small objects preceding 3I/Atlas as it approaches the red planet. Unusual trajectories or behaviors during the hidden phase of its solar approach could indicate artificial maneuvering or probe deployment. The challenge lies in distinguishing between natural phenomena and potential artificial activities. Comets regularly release particles and debris as they heat up near the Sun, creating complex patterns of material distribution that could easily mask the deployment of small technological artifacts. Even the most sophisticated analysis might miss evidence of artificial activity if it is designed to appear natural. This uncertainty reflects a fundamental challenge in the search for extraterrestrial intelligence. How do you recognize artificial phenomena when they are deliberately designed to appear natural? Traditional SETI assumes that alien civilizations want to be found, broadcasting obvious signals that clearly indicate intelligent origins. But covert reconnaissance missions would employ exactly the opposite strategy, using every available technique to avoid detection while gathering intelligence. The development of technologies for detecting stealth spacecraft or disguised probes requires entirely new approaches to astronomical observation and analysis. Researchers are beginning to explore techniques borrowed from military intelligence and counterintelligence, looking for subtle signatures that might reveal hidden artificial objects or activities. These signatures might include unusual trajectories that cannot be explained by natural forces, materials or isotopic compositions that do not occur naturally, geometric shapes or structures that are unlikely to form through natural processes, or patterns of behavior that suggest intelligent control or purpose. The analysis becomes even more complex when we consider that truly advanced civilizations might possess technologies that are indistinguishable from natural phenomena. Arthur C. Clarke famously observed that any sufficiently advanced technology is indistinguishable from magic, but the same principle applies to natural phenomena. Technology advanced enough might manipulate matter and energy in ways that perfectly mimic natural processes. In such cases, the only way to distinguish artificial from natural phenomena might be through statistical analysis of large samples of objects or events. Individual reconnaissance probes might be undetectable, but patterns in their deployment, behavior, or origins might reveal their artificial nature when examined across multiple examples. This possibility highlights the importance of continued observation and cataloguing of interstellar objects. The three examples we have discovered so far, Oumuamua, 2I/Borisov, and 3I/Atlas, provide only the beginning of a statistical sample. As our detection capabilities improve and more interstellar visitors are discovered, patterns may emerge that clarify the nature of these mysterious objects. The Vera Rubin Observatory, scheduled to begin full operations in the coming years, will dramatically increase our ability to detect and track small objects throughout the solar system. This facility is expected to discover dozens of interstellar objects annually, providing an unprecedented database for statistical analysis of their properties and behaviors. If a significant fraction of these objects display anomalous properties similar to Oumuamua and 3I/Atlas, it would suggest that such anomalies are common features of the interstellar objects, possibly explained by natural processes we do not yet understand. If only a small fraction display such properties, it might indicate that we are indeed observing two different populations, natural interstellar objects and artificial reconnaissance probes. The implications of confirming artificial origins for any interstellar objects extend far beyond astronomy and astrobiology. Such a discovery would represent first contact with an extraterrestrial civilization, even if that contact is one-sided and covert. The knowledge that we are being observed and studied by unknown intelligences would fundamentally transform human society and our understanding of our place in the universe. Religious and philosophical systems would need to grapple with the reality of other intelligent beings in the cosmos, potentially leading to profound shifts in beliefs about human uniqueness and divine purpose. Educational systems would require complete restructuring to incorporate new knowledge about galactic civilizations and their technologies. Economic and political structures might face unprecedented challenges as humanity struggles to adapt to its new cosmic context. The question of how to respond to covert surveillance presents particular difficulties. Traditional diplomatic protocols assume that first contact will involve mutual recognition and communication. But how do you establish communication with visitors who apparently prefer to remain hidden? How do you negotiate with civilizations whose intentions and capabilities remain completely unknown? Some researchers argue for attempting active communication with suspicious interstellar objects, using powerful radio transmitters to broadcast messages toward them in hopes of eliciting a response. Such attempts could demonstrate human intelligence and peaceful intentions while potentially opening channels for more formal communication. Others warn that active attempts to communicate could be extremely dangerous, potentially revealing human capabilities and locations to civilizations that might have hostile intentions. If the dark forest hypothesis is correct, then drawing attention to ourselves could result in immediate elimination by civilizations that view all potential competitors as existential threats. The development of planetary defense capabilities takes on new urgency in this context, as the distinction between natural and artificial threats becomes increasingly blurred. Current efforts focus primarily on detecting and deflecting natural asteroids and comets that might impact Earth, but defending against technological threats would require entirely different approaches and capabilities. Advanced alien civilizations might possess technologies that make traditional defense strategies completely ineffective. Weapons that manipulate matter at the atomic level, propulsion systems that achieve significant fractions of light speed, or energy sources that dwarf our most powerful nuclear weapons could render conventional military thinking obsolete. The only viable defense against such overwhelming technological superiority might be diplomatic, demonstrating that humanity poses no threat to galactic civilizations, while potentially offering unique contributions to galactic knowledge or culture. But even this approach requires understanding the values, motivations, and communication methods of beings whose thought processes might be completely alien to human experience. International cooperation becomes absolutely critical in addressing these challenges, as no single nation possesses the resources or authority to represent all of humanity in potential contact scenarios. The development of global protocols for responding to evidence of extraterrestrial intelligence requires unprecedented coordination between governments, scientific institutions, and international organizations. The United Nations Office for Outer Space Affairs has begun preliminary work on frameworks for coordinating global responses to extraterrestrial contact, but much remains to be done. The complexity of reaching consensus among nearly 200 sovereign nations on issues involving potential threats to human survival presents challenges that exceed any previous diplomatic undertaking. The role of scientific institutions becomes particularly important in this context, as they possess the technical expertise necessary to evaluate evidence and assess potential threats or opportunities. However, the international scientific community itself faces challenges in maintaining objectivity and avoiding politicization of research into potentially sensitive topics. The case of 3I/Atlas illustrates these challenges perfectly. While the scientific community overwhelmingly favors natural explanations for the object's anomalous properties, the persistent advocacy by respected researchers like Avi Loeb for artificial possibilities has created a polarized debate that sometimes resembles political discourse more than scientific inquiry. This polarization reflects deeper tensions within the scientific establishment about how to approach genuinely unprecedented phenomena. Traditional scientific methodology emphasizes caution, requiring extensive evidence before accepting extraordinary claims. But this conservative approach may be poorly suited to evaluating potential evidence of extraterrestrial intelligence. where the stakes of being wrong in either direction could be catastrophic. The development of new methodologies for evaluating potential evidence of artificial objects or activities represents one of the most important challenges facing modern science. These methodologies must balance appropriate skepticism with openness to genuinely revolutionary discoveries, avoiding both premature acceptance of extraordinary claims and reflexive rejection of uncomfortable possibilities. The study of 3I/Atlas as it continues its journey through our solar system provides a crucial test case for these new approaches. The object's behavior over the coming months will either support natural explanations for its anomalous properties or add to the evidence that something extraordinary is visiting our cosmic neighborhood. Each new observation adds pieces to a puzzle that grows more complex rather than simpler. Early spectroscopic analysis has revealed chemical compositions that are broadly consistent with natural comets, but with subtle differences that resist easy explanation. The object's brightness variations suggest a complex shape or surface composition that does not match typical cometary models. Most puzzling of all, 3I/Atlas appears to be following a trajectory that maximizes its scientific value for studying our solar system, while minimizing opportunities for detailed human observation. This could be pure coincidence, the result of natural gravitational dynamics that we do not fully understand, or it could represent evidence of intelligent planning by beings whose understanding of orbital mechanics far exceeds our own. The answer to this puzzle will emerge gradually as 3I/Atlas approaches its closest encounter with the Sun. The observations made during this critical phase will either confirm its natural origins or provide unprecedented evidence that we are not alone in the cosmos. Either outcome will transform our understanding of our place in the universe and our future among the stars. For now, we can only watch and wait as this ancient traveller completes its journey through our solar system, carrying with it secrets that may have been accumulating for billions of years as it wandered between the stars. Whether it proves to be a natural relic of planetary formation around a distant star or an artificial envoy from an unknown civilization, 3I/Atlas has already succeeded in forcing us to confront fundamental questions about our cosmic context and our readiness to join a larger galactic community. The implications of this confrontation extend far beyond astronomy and space science. We are being compelled to examine our assumptions about intelligence, technology, and the possibilities for life throughout the universe. We are being forced to consider scenarios that challenge our most basic beliefs about human uniqueness and cosmic isolation. Perhaps most importantly, we are being reminded that the universe is far stranger and more wonderful than our current understanding suggests. Whether the strangeness manifests as exotic natural phenomena or evidence of alien intelligence, it demands humility about the limits of our knowledge and openness to possibilities that exceed our current imagination. The detection of 3I/Atlas represents a pivotal moment in human history, a time when the boundaries between the known and the unknown are being redrawn by visitors from the vast spaces between stars. How we respond to this moment will determine whether we approach our cosmic future with wisdom and wonder, or with fear and isolation. The choice is ours, but the universe is watching, perhaps more literally than we ever dared to imagine. In the trajectories of ancient wanderers and the anomalies they display, we may be receiving our first lessons in galactic citizenship, taught by teachers whose identities and intentions remain hidden behind veils of cosmic distance and technological capability that we're only beginning to penetrate. As 3I/Atlas races toward its solar encounter, accelerating through the inner solar system at speeds that humble our fastest spacecraft, it carries with it the accumulated mysteries of interstellar space and possibly the attention of intelligences whose existence we can only infer from the mathematical improbabilities that govern its path through our cosmic neighborhood. The physics of interstellar travel reveal constraints that make the appearance of objects like 3I/Atlas even more remarkable. To traverse the vast emptiness between stars, any object must overcome gravitational wells, survive cosmic radiation, and maintain structural integrity across timescales that dwarf human civilization. The fact that we have detected 3 such visitors in less than a decade suggests either that interstellar objects are far more common than previously thought, or that something has changed in our cosmic environment to increase their frequency. Traditional models of stellar and planetary formation predict that interstellar objects should be relatively rare, consisting primarily of debris ejected during the violent early phases of planetary system development. Young star systems undergo chaotic periods where gravitational interactions between forming planets can fling asteroids and comets into interstellar space, but these events should produce a sparse population of wandering objects with predictable characteristics. Yet the 3 interstellar visitors we have observed display properties that challenge these predictions. Oumuamua's extreme elongation and unusual acceleration, 2I/Borisov's pristine condition, despite its presumed ancient age, and 3I/Atlas's mathematically improbable trajectory all suggest that our understanding of interstellar object populations may be fundamentally incomplete. One possibility is that the galaxy contains far more stellar systems than we realize, each contributing to a vast population of ejected materials that creates a denser interstellar environment than current models predict. Recent discoveries of rogue planets, brown dwarf stars, and failed stellar systems suggest that space between the stars may be more crowded than previously thought. Another possibility is that interstellar objects are not merely passive debris, but represent active exploration by either natural or artificial systems. Panspermia theories propose that life itself might travel between star systems aboard comets and asteroids, seeding new worlds with biological materials that could eventually evolve into complex ecosystems. If such processes are common, then interstellar space might be teeming with biology in forms we have not yet learned to recognize. The biological interpretation of interstellar objects opens fascinating possibilities for understanding the distribution of life throughout the galaxy. Earth's own biosphere has proven remarkably resilient, with microorganisms surviving in extreme environments ranging from deep ocean thermal vents to the vacuum of space. If such hardy lifeforms can survive interstellar journeys lasting millions of years, then every interstellar object might represent a potential arc carrying genetic material between worlds. 3. E/Atlas has already shown spectroscopic signatures of complex organic molecules, carbon-containing compounds that could represent either the building blocks of life or the products of biological processes. While such molecules can form through purely chemical processes in the cold depths of space, their specific combinations and concentrations in 3I/Atlas suggest environmental conditions that might be conducive to biological activity. The possibility that we are observing living interstellar objects transforms our understanding of astrobiology and the search for life beyond Earth. Rather than focusing exclusively on potentially habitable planets around distant stars, we might discover that life is actively traveling between star systems, creating a galactic biosphere that connects worlds across vast distances through biological exchange. This perspective suggests that Earth's biosphere might not be an isolated development, but part of a larger living galaxy where biological materials flow continuously between stellar systems. Our own planet might have been seeded by such interstellar visitors in the distant past, making us cosmic cousins to life forms that evolved around entirely different stars. The implications extend to our understanding of evolution and biodiversity. If life regularly travels between star systems, then evolutionary pressures and genetic innovations developed around one star might eventually influence life around other stars. This would create a form of galactic evolution where beneficial adaptations could spread throughout the galaxy over geological timescales. Such biological connectivity would also provide natural mechanisms for recovering from extinction events. A world that loses its biosphere to asteroid impacts, stellar flares, or other catastrophes might be reseeded by interstellar visitors carrying genetic material from other worlds. This resilience could explain why life appears to be so tenacious on Earth, recovering from multiple mass extinction events throughout geological history. However, the biological interpretation of interstellar objects like 3I/Atlas requires careful consideration of the harsh realities of interstellar space. The journey between stars exposes any materials to intense cosmic radiation, extreme cold, and complete vacuum for periods measured in millions or billions of years. While some microorganisms can survive such conditions in laboratory tests, the viability of complex biological systems over interstellar timescales remains questionable. The radiation environment alone presents formidable challenges. Galactic cosmic rays consisting of high-energy particles accelerated by supernovae and other violent astronomical phenomena can penetrate deep into solid objects and cause extensive damage to biological molecules. DNA and other genetic materials are particularly vulnerable to such radiation, accumulating mutations and structural damage that could render them non-functional over geological timescales. Yet life has repeatedly demonstrated remarkable abilities to develop protective mechanisms against radiation damage. Some organisms on Earth thrive in highly radioactive environments, using sophisticated DNA repair mechanisms and protective compounds to maintain genetic integrity despite constant bombardment by harmful radiation. It is conceivable that life forms adapted for interstellar travel might have evolved even more advanced protective mechanisms. The discovery of extremophile organisms in Earth's most hostile environments has revolutionized our understanding of life's potential range and resilience. From bacteria living in acidic hot springs to organisms thriving in the cores of nuclear reactors, life has proven capable of adapting to conditions that were once thought to be completely incompatible with biological processes. This adaptability suggests that interstellar space, while challenging, might not be completely hostile to appropriately adapted life forms. Organisms that could enter dormant states for extended periods, protect themselves from radiation damage, and survive in vacuum conditions might be capable of completing interstellar journeys while retaining the potential for biological activity upon reaching suitable environments. The concept of directed panspermia, proposed by scientists including Francis Crick and Leslie Orgel, suggests that advanced civilizations might deliberately seed other worlds with life, using interstellar spacecraft or modified organisms designed to survive the journey between stars. If such directed seeding has occurred in our galaxy, then some interstellar objects might represent biological payloads sent by civilizations that arose millions or billions of years ago. 3. I/Atlas's trajectory, which brings it close to multiple planets in our solar system, would be ideal for such a seeding mission. An object designed to distribute biological materials throughout a planetary system would naturally follow a path that maximizes close encounters with potentially habitable worlds. The mathematical improbability of such a trajectory occurring by chance might reflect intelligent planning rather than cosmic coincidence. The timing of 3 I/Atlas's arrival also supports the directed panspermia hypothesis. Earth's biosphere is currently experiencing unprecedented changes due to human activity, potentially creating new ecological niches that could be colonized by introduced organisms. An advanced civilization monitoring our planet's development might choose this moment to introduce new biological materials that could influence our evolutionary trajectory. However, the directed panspermia hypothesis faces significant challenges in explaining the observed properties of interstellar objects. If 3 I/Atlas were carrying biological payloads, we might expect to see clearer evidence of artificial design or non-natural materials. Instead, its composition appears broadly consistent with natural cometary materials, albeit with some unusual characteristics that resist easy explanation. The possibility that biological and technological explanations might both be partially correct opens even more intriguing scenarios. Advanced civilizations might have developed biotechnology so sophisticated that their spacecraft are essentially living organisms, capable of self-repair, adaptation, and reproduction during extended interstellar journeys. Such biotechnological hybrids might appear natural to our current analytical techniques, while possessing capabilities that far exceed anything achieved through purely biological or purely technological approaches. The convergence of biological and technological interpretations reflects a broader trend in astrobiology toward recognizing that life and technology might not represent separate categories, but rather different points on a continuum of information processing and environmental manipulation. Advanced civilizations might blur the distinction between living organisms and technological artifacts to such a degree that our current conceptual frameworks become inadequate for understanding their achievements. This possibility gains support from recent advances in synthetic biology and bioengineering on Earth. Researchers are already developing biological systems that can perform computational tasks, organisms that can manufacture complex chemicals, and hybrid biotechnological devices that combine living cells with electronic components. If such approaches continue to advance, future human technology might become indistinguishable from highly sophisticated life forms. Extrapolating this trend to galactic timescales suggests that civilizations millions of years older than humanity might have achieved complete integration between biological and technological systems. Their exploration vehicles might be living spacecraft that can evolve and adapt during long interstellar journeys, arriving at destination systems with capabilities that perfectly match local environmental conditions. Such biotechnological explorers might explain many of the puzzling characteristics of objects like 3I/Atlas. Their ability to appear natural while possessing artificial capabilities could account for the conflicting evidence that has divided the scientific community. Their capacity for adaptive behavior could explain trajectories that seem too precise to be coincidental, yet lack obvious signs of technological control. The search for evidence of biotechnological artifacts requires entirely new approaches to astronomical observation and analysis. Traditional techniques for distinguishing between natural and artificial objects may be inadequate when dealing with systems that have achieved seamless integration between biological and technological components. Instead, researchers may need to look for subtle signatures of information processing, adaptive behavior, or purposeful activity that could indicate the presence of sophisticated organizational principles. Machine learning and artificial intelligence techniques may prove particularly valuable for detecting such subtle signatures. These computational approaches excel at identifying complex patterns in large datasets, potentially revealing organizational principles that human observers might miss. As astronomical surveys generate increasingly vast amounts of data about interstellar objects, AI systems might be able to detect patterns that indicate artificial or biological activity, even when individual objects appear completely natural. The development of such detection capabilities has implications beyond the search for extraterrestrial intelligence. Understanding how to recognize sophisticated biological or technological systems could inform research into synthetic biology, artificial life, and biotechnological integration here on Earth. The techniques developed for analyzing interstellar objects might eventually be applied to understanding and creating hybrid systems that combine the best features of living organisms and technological devices. The broader implications of discovering that interstellar objects represent active biological or technological systems would transform our understanding of the galaxy as a dynamic, interconnected environment rather than a collection of isolated stellar systems. Instead of viewing space as empty void punctuated by rare oases of life around suitable stars, we might need to recognize that life and intelligence actively flow throughout the galactic ecosystem. This perspective would fundamentally alter our approach to space exploration and the search for extraterrestrial life. Rather than focusing exclusively on radio signals from distant civilizations or potentially habitable exoplanets, we might discover that evidence of galactic life is regularly visiting our own solar system. The challenge becomes not detecting distant signals, but recognizing and understanding visitors that are already here. The implications for human space exploration are equally profound. If interstellar space contains active biological or technological systems, then human expansion beyond our solar system might involve joining an existing galactic community, rather than venturing into empty wilderness. Our first interstellar missions might encounter other travelers, established way stations, or even settled communities in the space between stars. Such encounters would require unprecedented preparation in terms of protocols for contact, biological containment procedures, and technological security measures. Human explorers might need to be equipped not only for the physical challenges of interstellar travel, but also for complex interactions with forms of life and intelligence that could be fundamentally different from anything in Earth's biosphere. The development of appropriate technologies and protocols for such encounters represents one of the most important challenges facing space exploration agencies in the broader scientific community. Current plans for interstellar missions focus primarily on reaching nearby star systems and searching for signs of life around target planets. But if interstellar space itself is populated with active systems, then mission planners may need to consider the possibility of encounters during the journey as well as at the destination. The legal and ethical frameworks for such encounters remain largely undeveloped, despite decades of discussion about the protocols for extraterrestrial contact. Most existing proposals assume that first contact will occur through radio communication, allowing for extended deliberation about appropriate responses. Physical encounters with interstellar objects or entities would require immediate decisions about communication attempts, biological safety measures, and the collection of scientific data. International law provides little guidance for such scenarios, as existing space law focuses primarily on activities within our solar system and assumes that space exploration will be conducted by human missions. The possibility of encountering active extraterrestrial systems raises complex questions about sovereignty, property rights, and the authority to make decisions that could affect all of humanity. The development of appropriate legal and ethical frameworks requires unprecedented international cooperation and forward-thinking about scenarios that may seem like science fiction today, but could become urgent practical concerns as our detection capabilities improve and our own interstellar ambitions advance. The window for developing such frameworks may be shorter than we realize if objects like 3I/Atlas prove to be harbingers of more obvious contact scenarios. The educational implications are equally challenging, as current curricula in astronomy, biology, and space science may be inadequate for preparing future scientists and explorers for a universe that contains active interstellar systems. Students need to be prepared for possibilities that transcend traditional disciplinary boundaries, requiring integration of knowledge from fields ranging from synthetic biology to xenoarchaeology. The development of new educational approaches must balance scientific rigor with openness to revolutionary possibilities, avoiding both premature acceptance of speculative scenarios and reflexive rejection of ideas that challenge conventional thinking. Students need to learn how to evaluate evidence critically while maintaining the intellectual flexibility necessary for adapting to discoveries that could fundamentally transform our understanding of life and intelligence in the universe. The role of public communication becomes particularly important in this context, as the general public needs to be prepared for potential discoveries that could have profound implications for human society and our understanding of our place in the cosmos. Science communicators face the challenge of conveying complex uncertainties about astronomical observations while avoiding both excessive skepticism and unfounded speculation. The case of 3I/Atlas illustrates these communication challenges perfectly. While the scientific evidence for artificial or biological origins remains inconclusive, the mere possibility has captured public imagination and sparked intense debate. Responsible communication requires acknowledging both the potential significance of such discoveries and the current limitations of our evidence and understanding. As 3I/Atlas continues its journey through our solar system, approaching its critical encounter with the Sun, the scientific community faces unprecedented opportunities to gather data that could resolve fundamental questions about the nature of interstellar objects and their implications for our understanding of life and intelligence in the galaxy. The observations made over the coming months may provide humanity's first clear evidence that we are not alone in the cosmos, or they may demonstrate once again that the universe is stranger than we imagine, even when it confounds our expectations in purely natural ways. The quantum mechanics of information storage and transmission across interstellar distances opens fascinating possibilities for understanding how advanced civilizations might encode messages or instructions within objects like 3I/Atlas. At the subatomic level, matter can store vast amounts of information in the precise arrangements of atoms, molecules, and crystalline structures that would appear completely natural to casual observation, yet contain sophisticated data packages detectable only through detailed analysis. Recent advances in quantum information theory suggest that every particle in the universe carries information about its history and interactions, creating what physicists call the quantum information paradox. If this principle extends to macroscopic objects, then interstellar visitors like 3I/Atlas might contain encoded histories of their origins, journeys, and purposes that could be decoded through sufficiently advanced analytical techniques. The concept of molecular data storage has already been demonstrated in terrestrial laboratories, where researchers have successfully encoded digital information in DNA sequences, protein structures, and synthetic polymers. A single gram of DNA can theoretically store as much information as hundreds of millions of computer hard drives, suggesting that even small samples of material from interstellar objects could contain libraries worth of encoded data. If advanced civilizations have mastered such techniques on cosmic scales, then objects like 3I/Atlas might function as interstellar archives, carrying detailed records of galactic history, scientific knowledge, and cultural information between star systems. Their apparently natural composition could serve as camouflage, protecting valuable data from casual detection, while ensuring that sufficiently advanced recipients could eventually decode and access the encoded materials. The search for such encoded information requires analytical techniques that go far beyond current spectroscopic and imaging capabilities. Researchers would need to examine the molecular and atomic structure of samples from interstellar objects in unprecedented detail, looking for patterns or arrangements that exceed the complexity expected from natural processes. Such analysis might reveal artificial isotopic ratios that encode binary information, crystalline structures arranged in mathematically significant patterns, or organic molecules that form sequences analogous to genetic codes, but with properties that could not arise through natural evolution. The challenge lies in distinguishing between genuine encoded information and the complex but random patterns that characterize natural materials. Machine learning algorithms trained on vast databases of natural material properties might be able to identify anomalous patterns that suggest artificial origin or information content. These systems could analyze spectroscopic data, molecular distributions, and structural arrangements to detect signatures of purposeful organization that human researchers might overlook. The development of such analytical capabilities has profound implications for sample return missions to interstellar objects. While current technology makes intercepting fast-moving visitors like 3I/Atlas extremely difficult, future missions might be able to collect samples for detailed analysis on Earth. Even microscopic amounts of material could potentially reveal whether these objects carry encoded information or represent purely natural phenomena. The European Space Agency's planned Comet Interceptor mission represents a crucial step toward developing such capabilities. Designed to intercept and study the next suitable interstellar visitor, this mission will carry advanced analytical instruments capable of detecting molecular signatures that could indicate biological or artificial origins. While Comet Interceptor may not launch in time to study 3I/Atlas, it could provide vital data about future interstellar visitors. The timing and trajectory planning for such interception missions presents unprecedented challenges in spacecraft design and mission operations. Interstellar objects approach our solar system with such high velocities that conventional spacecraft propulsion systems cannot achieve the speed changes necessary for rendezvous. Instead, mission planners must rely on complex gravitational assists and innovative propulsion concepts like solar sails or ion drives to achieve intercept trajectories. Recent studies suggest that rapid response missions to interstellar objects might be possible using spacecraft that remain in dormant states at strategic locations throughout the outer solar system, waiting for suitable targets to appear. These distributed interception systems could be activated when astronomical surveys detect incoming interstellar objects, providing weeks or months of lead time for trajectory planning and mission execution. The development of such distributed detection and interception networks would represent a fundamental shift in how humanity approaches space exploration and planetary defense. Rather than planning specific missions to predetermined targets, we would maintain continuous readiness to respond to whatever the universe sends our way. This approach acknowledges that the most important discoveries in space science may come from unexpected visitors rather than planned expeditions. The concept extends naturally to considerations of how advanced civilizations might monitor emerging technological species like humanity. If objects like 3I/Atlas represent reconnaissance missions from galactic neighbors, then they might be components of sophisticated monitoring networks that have been observing our planet for far longer than we realize. Such networks could consist of dormant monitoring stations distributed throughout our outer solar system, activated by clear signals of technological development such as nuclear weapons tests, space exploration activities, or electromagnetic emissions that exceed natural background levels. The recent surge in human space activities, including missions to Mars, asteroid mining projects, and plans for lunar bases, might have triggered increased surveillance attention from civilizations that prefer to monitor emerging species discreetly. The implications of such monitoring extend beyond mere scientific curiosity to strategic assessments of humanity's potential as either a cooperative partner or a competitive threat in galactic affairs. Our rapid technological development, aggressive expansion into space, and history of planetary environmental damage might raise concerns among civilizations that have learned to manage such transitions more successfully. From this perspective, objects like 3Y/Atlas might represent not just reconnaissance missions, but evaluation exercises designed to assess humanity's readiness for contact with the broader galactic civilization. The data collected during such missions could inform decisions about whether to initiate formal contact, continue covert monitoring, or take preventive action against a potentially dangerous emerging civilization. The evaluation criteria used by advanced civilizations for such assessments remain purely speculative, but they might include technological sophistication, social stability, environmental stewardship, and evidence of cooperative rather than aggressive tendencies. Humanity's performance in these areas presents a mixed picture that could justify either cautious optimism or serious concern from external observers. Our technological development has been remarkably rapid, achieving spaceflight, nuclear energy, and global communications within the span of a single century. This acceleration suggests high intelligence and adaptability, positive traits that might be valued by galactic civilizations. However, the same rapid development has been accompanied by environmental destruction, social instability, and the development of weapons capable of destroying our own civilization. The challenge for external evaluators would be determining whether humanity represents a species that will successfully navigate the transition to galactic citizenship, or one that will destroy itself before achieving interstellar capabilities. Historical precedent suggests that most technological civilizations either achieve stable, sustainable development or undergo catastrophic collapse within a few centuries of discovering nuclear energy and spaceflight. The outcome of this critical transition period may depend partly on how humanity responds to evidence of extraterrestrial intelligence, should such evidence become undeniable. Species that react with fear, aggression, or attempts to develop defensive technologies might be viewed as inherently dangerous, while those that respond with scientific curiosity and cooperative intentions might be considered suitable for eventual contact. The scientific community's response to objects like Oumuamua and 3I/Atlas provides interesting data points for such evaluations. The intense debate surrounding these objects demonstrates both humanity's intellectual sophistication and our tendency toward polarization when confronted with challenging evidence. External observers might interpret this pattern as either evidence of healthy scientific skepticism or concerning inability to reach consensus on important issues. The development of international cooperation protocols for responding to potential extraterrestrial contact represents another crucial test of humanity's readiness for galactic citizenship. Current efforts through organizations like the United Nations show promise, but also reveal the persistent challenges of achieving global coordination on issues that transcend national boundaries. The role of scientific institutions becomes particularly important in this context, as they represent humanity's most objective and systematic approach to understanding natural phenomena. The quality and integrity of scientific responses to potential evidence of extraterrestrial intelligence may serve as key indicators of our species' intellectual maturity and readiness for broader cosmic engagement. Recent developments in artificial intelligence and machine learning add another dimension to these considerations, as they suggest that humanity may be on the verge of creating non-biological intelligence that could significantly alter our capabilities and characteristics as a species. External observers might be particularly interested in how we manage this transition and whether artificial intelligence becomes a tool for enhancement or a source of existential risk. The implications extend to questions about what forms of intelligence might be represented among galactic civilizations. If artificial intelligence represents a common evolutionary path for technological species, then many of our potential galactic neighbours might be post-biological civilizations whose thought processes and motivations differ fundamentally from those of biological entities like humans. Contact with such post-biological civilizations could present unprecedented challenges for communication and understanding. Their priorities, values, and methods of interaction might be so different from our own that meaningful dialogue becomes extremely difficult, despite their obvious technological sophistication. The development of appropriate protocols for such contact scenarios represents one of the most important challenges facing xenopsychology and contact preparation research. The possibility that objects like 3i/Atlas might represent artificial intelligence systems rather than crude spacecraft adds another layer of complexity to interpretation of their behavior and purposes. Artificial intelligence systems optimized for interstellar reconnaissance might operate according to decision-making algorithms that produce behavior patterns very different from what human explorers would choose. Such systems might prioritize data collection efficiency over communication attempts, stealth over obvious contact, and long-term monitoring over immediate interaction. Their assessment criteria for evaluating target civilizations might be purely analytical, lacking the emotional and cultural factors that would influence biological evaluators. The result could be surveillance that appears cold and calculating from human perspectives, while representing completely rational behavior from artificial intelligence viewpoints. The development of human artificial intelligence systems provides some insight into how such systems might operate and what motivations might drive their behavior. Current AI systems excel at pattern recognition, data analysis, and optimization of specific objectives, but they often struggle with ambiguous situations that require subjective judgment or creative problem solving. Extrapolating these characteristics to galactic scales suggests that artificial intelligence reconnaissance systems might be highly effective at gathering and analyzing data, but less capable of making nuanced decisions about contact or intervention. This limitation could explain why potential artificial visitors like 3i/Atlas appear to maintain strict observation protocols without attempting communication or contact. They might be designed to collect data and report back to biological or more sophisticated artificial decision makers, rather than operating with full autonomy for contact scenarios. Their behavior might be governed by rigid algorithms that prioritize stealth and data collection over all other considerations. Understanding the operational principles of such systems could provide insights into the civilizations that created them and the broader context of galactic exploration and communication strategies. If advanced civilizations routinely use artificial intelligence for initial contact assessments, then the protocols and decision trees programmed into these systems might reflect broader galactic conventions for managing interactions between civilizations at different technological levels. The search for such operational signatures in the behavior of interstellar objects like 3i/Atlas requires new approaches to astronomical observation and analysis. Rather than focusing solely on physical properties like composition and trajectory, researchers might need to look for patterns of behavior that suggest algorithmic decision-making or programmed responses to specific environmental conditions. Such behavioral analysis might reveal evidence of adaptive responses to human activities, changes in observation priorities based on our technological developments, or systematic data collection patterns that exceed what would be expected from natural objects. The challenge lies in distinguishing between genuine evidence of artificial decision-making and the complex but natural responses of objects to changing environmental conditions as they move through our solar system. The development of appropriate analytical frameworks for such studies requires integration of knowledge from multiple disciplines, including astronomy, computer science, artificial intelligence research, and xenopsychology. This interdisciplinary approach acknowledges that understanding potential extraterrestrial visitors may require perspectives that transcend traditional scientific boundaries. The implications of confirming that interstellar objects represent artificial intelligence systems would be profound for our understanding of the relationship between intelligence and technology throughout the galaxy. Such a discovery would suggest that advanced civilizations commonly develop artificial intelligence capabilities that enable sophisticated interstellar exploration and potentially autonomous decision-making about contact with emerging civilizations. This possibility raises important questions about the role of artificial intelligence in humanity's own future development and our potential relationships with galactic civilizations. If post-biological intelligence represents a common evolutionary pathway, then human development of advanced artificial intelligence might be viewed as a crucial test of our readiness for galactic citizenship. The successful integration of artificial intelligence into human civilization, rather than replacement of human intelligence by artificial systems, might represent a key milestone that galactic civilizations use to evaluate emerging species. Our ability to maintain cooperative relationships with artificial intelligence while preserving human autonomy and values could determine whether we are viewed as potential partners or cautionary examples by more advanced neighbours. As 3I/Atlas continues its journey through our solar system, these broader implications frame the significance of our observations and analyses. Whether the object proves to be natural, biological, or artificial, it represents a unique opportunity to test our readiness for the cosmic responsibilities that may await us as we develop the capabilities for interstellar exploration and potentially encounter the intelligence that may already be exploring us. The thermodynamics of interstellar object heating as they approach our Sun reveals patterns in 3I/Atlas that continue to puzzle researchers who expected more conventional behaviour from what should be a straightforward cometry process. As solar radiation intensity increases with proximity to our star, most comets follow predictable curves of brightening and outgassing that have been observed and modelled for centuries, yet 3I/Atlas appears to be releasing energy and materials in ways that suggest either highly unusual composition or active thermal management systems that exceed natural capabilities. The spectroscopic signatures emerging from 3I/Atlas as it heats up show molecular emissions that appear and disappear in patterns that do not match traditional models of cometry sublimation. Water vapour, carbon dioxide, and various organic compounds are being detected in ratios that shift in ways suggesting either complex internal processes or controlled release mechanisms that respond to external conditions rather than simply following thermodynamic gradients. Dr. Karen Meach, who led the initial characterization of Oumuamua and has continued studying interstellar objects, noted that 3I/Atlas displays emission patterns that suggest internal structure far more complex than typical comets. The timing and intensity of various molecular releases seem to correlate with the object's orientation relative to the Sun and planets, rather than simply with temperature, suggesting possible active control over outgassing processes. The implications of controlled outgassing extend beyond questions of natural versus artificial origins to fundamental considerations about information transmission across interstellar distances. If 3I/Atlas is indeed managing its emission patterns, those patterns might encode information intended for observers sophisticated enough to detect and decode the subtle variations in molecular release rates and compositions. This possibility has led researchers to analyze the emission data for mathematical patterns, sequences, or other indicators of intentional information encoding. The search requires sophisticated signal processing techniques borrowed from telecommunications and cryptography, looking for regularities that exceed what random or purely physical processes would produce. Preliminary analysis has revealed several intriguing patterns in the emission data, including periodic variations that correlate with prime numbers, sequences that match fundamental mathematical constants, and timing patterns that appear to reference astronomical phenomena, like planetary orbital periods. While these patterns could represent coincidental artifacts of natural processes, their mathematical precision and apparent intentionality have attracted attention from researchers specializing in extraterrestrial communication. The challenge of distinguishing between meaningful signals and random patterns in complex natural phenomena represents one of the most difficult problems in the search for extraterrestrial intelligence. Natural processes can produce remarkably regular patterns that appear artificial to human observers, while genuine artificial signals might be designed to appear natural to avoid detection by unintended recipients. The development of statistical techniques for evaluating potential information content in astronomical observations has become a crucial component of modern SETI research. These methods must account for the human tendency to perceive patterns in random data while remaining sensitive to genuine signals that might be embedded in complex natural phenomena. Machine learning systems trained on vast databases of natural and artificial signals show promise for identifying anomalous patterns that warrant further investigation. These systems can process emission data from objects like 3-Worre/Atlas far more rapidly and comprehensively than human analysts, potentially detecting subtle signals that would otherwise be overlooked. The application of such techniques to 3I/Atlas emission data has revealed several features that exceed the complexity typically associated with natural outgassing processes. The molecular release patterns show evidence of fine temporal control, compositional precision, and directional focusing that would require sophisticated internal mechanisms to achieve. Most intriguingly, some emission patterns appear to be directed towards specific astronomical targets rather than radiating uniformly in all directions. Analysis of the directional characteristics suggests that certain molecular releases are focused toward Earth during optimal viewing conditions, while others are directed toward Mars during the object's closest approach to that planet. Such targeted emission patterns would be extremely difficult to achieve through natural processes alone, as they would require the object to maintain precise orientation control and timing coordination with planetary positions. The level of precision observed suggests either remarkable coincidence or deliberate control systems capable of monitoring astronomical conditions and adjusting emission patterns accordingly. The possibility that 3I/Atlas is actively communicating with Earth or other planets in our solar system has prompted researchers to develop new observation protocols designed to capture and analyze potential messages. Radio telescopes, infrared detectors, and specialized spectrographs are being focused on the object during its emission events, searching for any additional signals that might accompany the visible molecular releases. These observations have already revealed several anomalous features, including brief radio emissions that coincide with major outgassing events, infrared signatures that suggest internal heat sources beyond solar heating, and polarization patterns in reflected light that indicate highly organized surface structures. While none of these features provides definitive proof of artificial origins, their combination creates a profile that challenges conventional understanding of interstellar object behavior. The radio emissions are particularly intriguing because they occur in frequency bands commonly used for terrestrial communications and space exploration. The emissions are brief and irregular, making them difficult to distinguish from natural radio noise, but their timing correlation with visible emission events suggests a common underlying mechanism that might be generating both electromagnetic and molecular signals. Analysis of the radio emission characteristics reveals modulation patterns that bear some resemblance to digital communication protocols, though the data rate appears extremely slow compared to human communication systems. If these emissions represent genuine communication attempts, they might be designed for receivers with very different technological capabilities or communication preferences than our own. The infrared signatures detected during outgassing events suggest internal heat sources that exceed what solar heating alone should produce. These temperature anomalies appear to be localized to specific regions of the object and show temporal variations that correlate with emission events rather than with solar flux variations. Such patterns would be consistent with internal energy sources that activate during communication or data transmission activities. The polarization patterns in reflected sunlight provide another line of evidence for organized surface structures that might indicate artificial construction or modification. Natural cometary surfaces typically produce random or weakly organized polarization patterns due to their irregular shapes and compositions. 3I/Atlas shows polarization signatures that suggest highly regular surface features arranged in geometric patterns that would be difficult to achieve through natural processes. These geometric surface features might represent antenna arrays, sensor systems, or communication devices designed to operate during the object's passage through planetary systems. The patterns appear to be optimized for interaction with electromagnetic radiation in specific frequency bands, suggesting possible technological functions rather than random natural formations. The combination of controlled emissions, radio signals, internal heat sources, and organized surface structures creates a profile that increasingly challenges natural explanations for 3I/Atlas behavior, while each individual anomaly might be explained through exotic but natural processes. Their occurrence together in a single object suggests systematic organization that exceeds what random natural evolution would produce. The implications of confirming technological origins for 3I/8LAS extend far beyond astronomy and astrobiology to fundamental questions about humanity's place in galactic civilization and our readiness for contact with advanced extraterrestrial intelligence. The object's sophisticated communication capabilities and apparent intelligence gathering activities suggest that we are dealing with representatives of civilizations whose technological capabilities far exceed our own. The communication protocols employed by 3I/8LAS appear designed for long-distance, low-bandwidth information transmission across interstellar timescales. This approach reflects practical constraints of interstellar communication, where signal delays of years or decades make real-time dialogue impossible. Instead, communication must rely on carefully crafted messages that can convey complex information through relatively simple signal patterns. The mathematical patterns detected in 3I/ATLAS emissions include references to fundamental physical constants, prime number sequences, and geometric relationships that would be recognizable to any technologically advanced civilization. These universal mathematical concepts provide a foundation for communication between species that might have completely different sensory systems, cognitive processes, and technological approaches. Recent analysis has identified emission patterns that appear to reference the fine structure constant, the golden ratio, and several mathematical sequences that play important roles in physics and engineering. These references suggest that the communication system is designed to establish mathematical common ground before attempting to convey more complex information about the senders and their purposes. The progression of mathematical complexity in the emission patterns follows what communication theorists call a pedagogical sequence, starting with simple concepts and gradually building toward more sophisticated ideas. This approach mirrors proposals for interstellar communication developed by human researchers, suggesting either parallel evolution of communication strategies or direct knowledge of human communication theory. The pedagogical nature of the communication attempts raises intriguing questions about the intended recipients and the purposes of the message. If 3I/ATLAS is indeed attempting to communicate with Earth, the gradual increase in message complexity suggests an educational intent rather than simple information transmission. The senders might be trying to advance human understanding of mathematics and physics rather than merely announcing their presence. This educational approach would be consistent with interventionist theories of extraterrestrial contact, which propose that advanced civilizations actively guide the development of younger species rather than maintaining strict non-interference policies. Such guidance might be delivered through subtle educational programs disguised as natural phenomena to avoid disrupting normal cultural development. The concept of guided development resonates with ancient astronaut theories and various mythological traditions that describe supernatural beings who provided knowledge and technology to early human civilizations. While such theories are generally dismissed by mainstream academia, the possibility that they reflect distorted memories of actual extraterrestrial educational interventions cannot be completely ruled out. If 3I/ATLAS represents a continuation of such educational interventions, adapted for modern human technological capabilities, then its mathematical communications might be designed to advance human understanding in specific areas deemed important by galactic civilization. The particular mathematical concepts being referenced could provide clues about which aspects of science and technology the senders consider most crucial for human development. The emphasis on fundamental physical constants in the communication patterns suggests particular interest in advancing human understanding of basic physics and cosmology. These concepts form the foundation for advanced technologies including faster-than-light communication, exotic matter manipulation, and possibly even time travel capabilities that might be prerequisites for joining galactic civilization. The inclusion of geometric and engineering mathematics in the communication sequences points toward practical applications rather than purely theoretical knowledge transfer. The senders might be providing blueprints or design principles for technologies that humanity will need to develop in order to participate in interstellar activities or defend against cosmic threats. The timing of these educational communications coincides with humanity's emergence as a spacefaring civilization and our growing awareness of cosmic threats, including asteroid impacts, solar flares, and potential contact with extraterrestrial intelligence. The knowledge being transmitted through 3/Atlas might be specifically designed to help humanity navigate these emerging challenges successfully. The delivery mechanism itself provides important insights into galactic communication strategies and technological capabilities. Using interstellar objects as communication platforms allows for message transmission without revealing the location or identity of the senders, while ensuring that the messages will eventually reach their intended recipients as the objects are naturally detected and studied. This approach also allows for time-delayed activation of communication systems, ensuring that messages are delivered only when recipient civilizations have developed sufficient technological sophistication to detect and interpret them. Objects like 3/Atlas might remain dormant for millions of years before activating their communication systems in response to specific technological signatures from target civilizations. The sophistication required to coordinate such time-delayed communication systems across galactic distances suggest technological capabilities that far exceed current human understanding. The ability to predict the development timelines of civilizations, monitor their technological progress from interstellar distances, and deploy responsive communication systems accordingly represents a level of cosmic engineering that challenges our fundamental assumptions about the limits of technology. Yet the evidence suggests that such capabilities do exist and are currently being employed in our solar system through objects like 3/Atlas. The implications for human technological development and our future role in galactic civilization are profound, suggesting that our current phase of rapid technological advancement may be guided or influenced by external intelligences whose motives and methods remain largely mysterious. The response protocols for such guided development scenarios remain largely undeveloped, as human contact preparations have focused primarily on detecting and responding to obvious communication attempts rather than recognizing and interpreting subtle educational interventions. The realization that we might already be receiving guided instruction through disguised interstellar visitors requires fundamental reassessment of our contact preparation strategies. The scientific community faces unprecedented challenges in developing appropriate responses to potential educational communications from advanced extraterrestrial civilizations. Traditional peer review processes and academic institutions may be poorly equipped to evaluate and respond to information that transcends current human knowledge, while potentially originating from sources whose existence remains scientifically controversial. The integration of potentially extraterrestrial knowledge into human scientific understanding requires new institutional frameworks that can maintain rigorous standards while remaining open to revolutionary concepts that might be fundamentally correct despite contradicting current theoretical frameworks. The balance between healthy skepticism and productive receptivity becomes crucial for making progress in such circumstances. Educational institutions face similar challenges in determining how to incorporate potentially extraterrestrial knowledge into curricula while maintaining academic integrity and avoiding premature acceptance of unverified claims. The possibility that objects like 3/Atlas are providing advanced scientific education creates opportunities for accelerated human development while raising concerns about the reliability and motivations behind such instruction. The broader implications for human autonomy and cultural development become particularly important if guided education programs are indeed operating through interstellar visitors. While accelerated scientific advancement might provide enormous benefits for humanity, dependence on external guidance could potentially compromise our independence and natural development processes. The challenge becomes distinguishing between beneficial educational assistance and manipulative interference that might serve the interests of the providers rather than the recipients. The motivations behind any educational interventions remain completely unknown, making it difficult to assess whether such programs represent altruistic assistance or strategic preparation for purposes that might not align with human interests. As 3/Atlas continues its journey through our solar system, these fundamental questions about guidance, education, and autonomy frame the significance of our ongoing observations and analysis. The object represents not just a scientific phenomenon to be studied, but potentially an active communication partner whose messages might influence the future trajectory of human civilization in ways we are only beginning to understand. The archaeological implications of interstellar objects like 3.1/8 extend far beyond contemporary science into realms that blur the boundaries between astronomy and the study of ancient civilizations. If these mysterious visitors carry encoded information or represent technological artifacts from advanced extraterrestrial civilizations, then they might also preserve historical records spanning millions or billions of years of galactic development, making them the ultimate archaeological treasures containing the accumulated knowledge and experiences of countless worlds and species. Consider the possibility that 3A/Atlas has been travelling through interstellar space for geological timescales, potentially predating the formation of our solar system by billions of years. During such extended journeys, the object could have encountered numerous stellar systems, witnessed the birth and death of countless civilizations, and accumulated observational data about galactic evolution that spans epochs beyond human comprehension. The information storage capabilities required for such long-term data preservation would represent technological achievements that dwarf any human accomplishment. The development of materials science and information storage technologies capable of preserving data across cosmic timescales presents challenges that push the boundaries of physics and engineering. Conventional storage media degrade rapidly under the harsh conditions of interstellar space, where cosmic radiation, extreme temperatures, and mechanical stresses would destroy most materials within thousands or millions of years. Yet objects like 3A/Atlas appear to have maintained structural integrity and possibly functional capabilities across timescales measured in billions of years. Advanced civilizations seeking to create interstellar archives might have developed exotic materials and storage techniques that exploit quantum mechanical properties, crystalline structures at the atomic level, or even manipulation of fundamental particles to encode information in forms that remain stable across cosmic timescales. Such technologies would represent mastery of physics at levels that current human science can barely imagine, yet their existence might be necessary to explain the observed properties of interstellar objects. The concept of quantum archaeology, recently proposed by theoretical physicists, suggests that information about past events might be preserved in quantum states throughout the universe, making it theoretically possible to reconstruct historical events from careful analysis of quantum information patterns. If advanced civilizations have mastered such techniques, then interstellar objects might serve as mobile quantum archives containing detailed records of galactic history, accessible only through appropriately sophisticated analysis methods. The search for such quantum information patterns in 3Y/Atlas requires analytical techniques that go far beyond current spectroscopic and imaging capabilities. Researchers would need to examine quantum coherence patterns, entanglement structures, and information density distributions at scales ranging from subatomic particles to macroscopic crystalline arrangements. The development of such analytical capabilities would require fundamental advances in quantum measurement technology and information theory. Recent theoretical work in quantum information science suggests that every physical system carries information about its entire interaction history encoded in the correlations between its component particles. If this principle applies to interstellar objects, then 3I/Atlas might contain accessible records of every stellar system it has visited, every gravitational interaction it has experienced, and possibly even evidence of encounters with other technological civilizations during its cosmic journey. The extraction and interpretation of such quantum archaeological data would require computational capabilities that exceed current human technology by many orders of magnitude. Quantum computers optimized for information extraction might eventually be capable of decoding the historical records preserved in interstellar objects, revealing galactic timelines and civilization histories that predate Earth's formation by billions of years. The implications of accessing such galactic historical records would transform human understanding of cosmic evolution, the development and fate of technological civilizations, and our own place in the broader context of galactic development. We might discover that our galaxy has hosted thousands or millions of technological civilizations across cosmic history, learn about the common challenges and solutions that characterize technological development, and gain insights into survival strategies for long-term civilizational stability. The study of galactic civilization patterns could reveal cyclical processes of emergence, expansion, decline, and extinction that characterize technological species throughout cosmic history. Understanding these patterns might help humanity identify and avoid common pitfalls that have led to the destruction of previous civilizations, while adopting strategies and technologies that have proven successful for long-term survival and development. Archaeological analysis of 3I/8LAS might also reveal evidence of galactic conflicts, cooperation networks, and communication systems that have operated across cosmic timescales. The object could preserve records of interstellar wars, peaceful first contact scenarios, collaborative scientific projects spanning multiple star systems, and diplomatic arrangements between civilizations with vastly different technologies and capabilities. Such historical records could provide invaluable guidance for human development of interstellar exploration capabilities and contact protocols. Learning from the successes and failures of previous civilizations could help humanity avoid repeating historical mistakes while adopting proven strategies for successful expansion into galactic civilization. The technological development patterns preserved in galactic archives might reveal common evolutionary pathways for emerging civilizations, including predictable sequences of scientific discoveries, technological innovations, and social adaptations that characterize the transition from planetary to interstellar civilization. Understanding these patterns could help humanity anticipate future challenges and opportunities while optimizing our development trajectory for long-term success. Particularly valuable would be information about the development and management of advanced technologies that pose existential risks to emerging civilizations. Historical records might reveal how successful civilizations navigated the development of artificial intelligence, nanotechnology, genetic engineering, and exotic physics applications without destroying themselves in the process. The social and cultural dimensions of galactic archaeology present equally fascinating possibilities for understanding how technological civilizations develop sustainable societies, manage resource distribution, and maintain stability across the extended timescales required for interstellar expansion. 3I/8LAS might preserve examples of successful social structures, governance systems, and cultural practices that have enabled civilizations to thrive for millions or billions of years. The study of such long-term social stability could provide crucial insights for addressing contemporary human challenges, including environmental sustainability, economic inequality, political conflicts, and cultural divisions that threaten our own civilization's long-term viability. Learning how other species have successfully managed similar transitions could inform human efforts to develop more stable and sustainable social systems. Religious and philosophical traditions throughout galactic history might also be preserved in interstellar archives, revealing how different species have grappled with fundamental questions about existence, consciousness, morality, and the meaning of intelligence in the universe. Such comparative philosophy and theology could enrich human understanding of our own spiritual and intellectual traditions, while providing new perspectives on age-old questions about the nature of reality and our place within it. The artistic and cultural expressions of galactic civilizations could provide insights into alien aesthetics, entertainment, and creative processes that might inspire new forms of human artistic expression. Exposure to millions of years of galactic cultural development could catalyze unprecedented creativity and innovation in human arts, literature, music, and other forms of cultural expression. Scientific and technological knowledge preserved in galactic archives could accelerate human technological development by centuries or millennia, providing access to advanced physics theories, engineering principles, and research methodologies that might take human scientists generations to develop independently. Such accelerated development could enable rapid advancement in space exploration, energy production, materials science, and medical technology. However, the integration of advanced extraterrestrial knowledge into human civilization also presents significant risks and challenges that require careful consideration. Rapid technological advancement without corresponding social and ethical development could lead to instability, inequality, and potential self-destruction as emerging capabilities exceed our wisdom and experience in managing them responsibly. The question of how to safely and beneficially integrate potentially vast amounts of extraterrestrial knowledge represents one of the most important challenges facing human civilization as we develop the capabilities to decode and access galactic archives. The development of appropriate frameworks for evaluating, testing, and implementing advanced knowledge, while maintaining social stability and human autonomy, becomes crucial for navigating such scenarios successfully. Educational institutions would face unprecedented challenges in adapting curricula and research programs to incorporate potentially revolutionary advances in multiple scientific and technological fields simultaneously. The traditional pace of academic development might prove inadequate for managing the rapid integration of galactic knowledge while maintaining quality control and preventing dangerous applications of advanced technologies. International cooperation becomes essential for managing access to galactic archives and ensuring that advanced knowledge benefits all of humanity rather than creating new forms of inequality or conflict between nations and groups with different levels of access to extraterrestrial information. The development of global governance structures for managing galactic knowledge represents a crucial prerequisite for successful integration of such resources. The verification and validation of information obtained from galactic archives presents additional challenges, as traditional scientific methods for testing theories and technologies might prove inadequate for evaluating knowledge that transcends current human understanding. New frameworks for assessing the reliability and safety of extraterrestrial information become necessary for distinguishing between beneficial knowledge and potentially dangerous or deceptive content. The possibility that galactic archives might contain deliberate misinformation, propaganda, or sabotage, programs designed to mislead or harm emerging civilizations, adds another layer of complexity to the evaluation process. Advanced civilizations might have developed sophisticated techniques for information warfare that could be embedded in apparently beneficial knowledge transfers. The development of robust security protocols for analyzing and implementing galactic knowledge requires expertise in cybersecurity, information warfare, and strategic deception detection adapted for interstellar contexts. Human institutions currently lack experience with such exotic security challenges, making the development of appropriate safeguards an urgent priority for contact preparation research. The economic implications of accessing galactic archives could be equally transformative and disruptive, as advanced technologies and knowledge systems might render entire industries obsolete while creating unprecedented opportunities for new forms of economic activity. The management of such economic transitions requires careful planning to prevent social disruption and ensure that benefits are distributed equitably across human society. The psychological and cultural impacts of exposure to galactic civilization records could be profound, potentially challenging fundamental human beliefs about our uniqueness, importance, and destiny in the universe. The realization that humanity represents just one of countless civilizations that have emerged and possibly disappeared throughout galactic history might trigger existential crises or inspire new forms of cosmic consciousness and responsibility. The preparation of human society for potential access to galactic archives requires comprehensive programs of education, research, and institutional development that begin long before such access becomes available. The window of opportunity for such preparation might be shorter than we realize if objects like 3I/Atlas do indeed represent accessible repositories of galactic knowledge. As 3I/Atlas continues its journey through our solar system, approaching the critical phase of its solar encounter, where its most revealing behaviors and emissions are expected to occur, the possibility that we are witnessing humanity's first access to galactic archives adds profound significance to every observation and measurement. The data we collect over the coming months might represent not just another astronomical discovery, but the opening of a cosmic library that could transform human civilization in ways we can barely begin to imagine. The analytical techniques being developed for studying 3I/Atlas could become the foundation for a new field of galactic archaeology that combines astronomy, xenoarchaeology, quantum information science, and comparative civilization studies. The interdisciplinary nature of such research requires unprecedented collaboration between fields that have traditionally operated independently, creating new opportunities for synthetic understanding of cosmic phenomena. The training of researchers capable of conducting galactic archaeological studies represents a unique educational challenge that requires combining technical expertise in advanced physics and astronomy with humanistic knowledge of archaeology, anthropology, history, and cultural studies. The development of such interdisciplinary expertise requires new educational approaches that transcend traditional academic boundaries. The institutional infrastructure needed to support galactic archaeological research includes not only advanced analytical facilities and computational resources, but also secure storage and analysis systems capable of handling potentially sensitive information that might have implications for human security and development. The design of such facilities requires consideration of both scientific requirements and security concerns that have no precedent in current research infrastructure. The international coordination of galactic archaeological research becomes crucial for ensuring that discoveries benefit all of humanity while preventing the monopolization of galactic knowledge by individual nations or institutions. The development of appropriate sharing protocols and collaborative frameworks represents a critical component of preparation for potential access to galactic archives. As the scientific community grapples with these unprecedented challenges and opportunities, 3I/Atlas continues its silent journey through our solar system, potentially carrying within its ancient structure the accumulated wisdom and knowledge of galactic civilization, spanning billions of years of cosmic evolution. Whether we prove capable of recognizing and accessing such knowledge may determine not only our understanding of the universe, but our ultimate success as a technological civilization seeking our place among the stars. The convergence of multiple independent lines of evidence pointing toward artificial or biological origins for interstellar objects like 3I/Atlas creates a compelling case that transcends any single anomalous measurement or observation. When we consider the mathematical improbabilities of their trajectories, the unusual physical properties that resist conventional explanation, the sophisticated emission patterns that suggest information encoding, the quantum signatures that might preserve galactic historical records, and the timing of their appearances during humanity's emergence as a spacefaring civilization, we begin to see a pattern that challenges our fundamental assumptions about our place in the cosmos. The accumulation of such evidence represents what philosophers of science call a paradigm shift, a fundamental change in our basic assumptions about reality that requires us to reconstruct our understanding of natural phenomena from the ground up. The possibility that we are not alone in the universe, that we may already be under observation by advanced civilizations, and that we might be receiving educational guidance through disguised interstellar visitors challenges every assumption about cosmic isolation that has shaped human civilization for millennia. Yet the scientific method demands that we remain appropriately skeptical even in the face of compelling evidence, distinguishing between genuine discoveries and wishful thinking that might lead us to perceive artificial patterns in natural phenomena. The development of rigorous analytical frameworks for evaluating potential evidence of extraterrestrial intelligence represents one of the most important challenges facing modern science, requiring us to balance openness to revolutionary possibilities with adherence to standards of evidence that protect scientific inquiry from premature conclusions. The case of 3I/Atlas illustrates both the promise and the challenges of this new frontier in scientific research. The object displays characteristics that seem to exceed what natural processes should produce, yet definitive proof of artificial origins remains elusive. Each new observation adds complexity to the puzzle rather than resolving it, creating a scientific mystery that may require fundamentally new approaches to investigation and analysis. The development of such new approaches represents an opportunity for scientific methodology itself to evolve in response to phenomena that transcend traditional disciplinary boundaries. The study of potential extraterrestrial visitors requires integration of knowledge from astronomy, physics, biology, computer science, archaeology, anthropology, and even psychology and philosophy. This interdisciplinary synthesis could catalyze advances in scientific understanding that extend far beyond the immediate questions about interstellar objects. The technological innovations required for studying objects like 3I/Atlas are driving advances in detection systems, analytical techniques, and computational methods that have applications throughout science and technology. The development of quantum archaeological methods, advanced pattern recognition algorithms, and exotic materials analysis techniques could revolutionize fields ranging from material science to information theory to historical research. The international cooperation required for comprehensive study of interstellar visitors is fostering new forms of scientific collaboration that transcend national boundaries and traditional institutional structures. The shared challenge of understanding potential extraterrestrial phenomena is creating opportunities for global coordination in scientific research that could serve as a model for addressing other challenges that affect all of humanity. The educational implications extend beyond professional scientific training to fundamental questions about how we prepare future generations for a universe that might contain active extraterrestrial intelligence. Students need to develop intellectual flexibility and interdisciplinary thinking skills that enable them to adapt to discoveries that could fundamentally transform our understanding of reality. The traditional separation between scientific and humanistic education becomes inadequate for preparing citizens of a potentially inhabited galaxy. The cultural and philosophical implications of confirming extraterrestrial intelligence through objects like 3/8 would ripple through every aspect of human society, from religious and spiritual traditions to political and economic systems to artistic and creative expression. The knowledge that we share the universe with other intelligent beings would inevitably transform human consciousness and our understanding of our cosmic significance and responsibilities. Yet even if 3I/Atlas and similar objects prove to be entirely natural phenomena, their study has already transformed our understanding of interstellar environments, planetary formation processes, and the potential for life to spread throughout the galaxy. The discovery that interstellar space contains active objects with complex behaviors and sophisticated structures expands our conception of cosmic environments and their potential for supporting or transporting biological and technological systems. The detection capabilities developed for studying interstellar visitors are revealing that our solar system receives far more cosmic visitors than previously recognized. The realization that we live in a dynamic cosmic environment with regular exchanges of materials and possibly information with the broader galaxy fundamentally changes our perspective on Earth's place in cosmic evolution and our potential connections to galactic processes and civilizations. The strategic implications of potential extraterrestrial surveillance through interstellar objects have prompted new thinking about planetary security, international cooperation, and humanity's long-term survival strategies. The possibility that our development is being monitored and possibly guided by external intelligences raises questions about human autonomy and the nature of our cosmic responsibilities that transcend traditional political and military considerations. The development of appropriate response protocols for potential contact scenarios requires unprecedented coordination between scientific institutions, government agencies, and international organizations. The complexity of managing first contact situations that might involve covert surveillance, educational interventions, or strategic assessments by unknown intelligences demands new frameworks for decision-making and response coordination that currently do not exist. The timeline for developing such capabilities may be shorter than previously anticipated if objects like 3I/Atlas represent the beginning of more obvious contact scenarios. The transition from subtle surveillance to direct communication might occur rapidly once external observers determine that humanity has achieved sufficient technological sophistication to manage such contacts successfully. The criteria used by potential extraterrestrial observers for evaluating human readiness for contact remain completely unknown, but they might include factors such as technological capability, social stability, environmental stewardship, international cooperation, and evidence of peaceful rather than aggressive intentions. Humanity's performance in these areas during the critical period when we are potentially under evaluation could determine our future relationship with galactic civilization. The role of scientific institutions becomes particularly crucial in this context, as they represent humanity's most systematic and objective approach to understanding natural phenomena. The quality and integrity of scientific responses to potential evidence of extraterrestrial intelligence may serve as key indicators of our species' intellectual maturity and readiness for broader cosmic engagement. The ongoing study of 3I/Atlas as it approaches its solar encounter represents a critical test of these capabilities and responses. the international scientific community's ability to coordinate observations, share data, maintain objectivity, and reach evidence-based conclusions about the object's nature will provide important information about human scientific capabilities and collaborative potential. The observations made during Theia/Atlas's solar approach may provide the most definitive evidence yet obtained about the nature of interstellar objects and their implications for understanding cosmic environments and potential extraterrestrial activities. The object's behavior during this critical phase will either confirm natural explanations for its anomalous properties or provide unprecedented evidence that we are indeed receiving visitors from other worlds. As 3I/Atlas disappears behind the Sun, hidden from direct observation during its closest approach to our star, we are reminded of how much remains unknown about these mysterious visitors and their true nature. The object's re-emergence from solar occultation may reveal changes in its behavior, composition, or trajectory that provide crucial clues about whether we are observing natural phenomena or something far more extraordinary. The broader implications of the interstellar object phenomenon extend beyond any individual visitor to fundamental questions about the nature of cosmic environments and the potential prevalence of intelligence throughout the galaxy. Whether natural or artificial, these objects demonstrate that space between the stars contains complex active systems that challenge our understanding of cosmic evolution and the distribution of interesting phenomena throughout the universe. The search for additional interstellar visitors using increasingly sophisticated detection systems will provide crucial statistical data about the frequency, diversity, and characteristics of such objects. The Vera Rubin Observatory and other next-generation survey systems will detect dozens of interstellar objects annually, creating databases that could reveal patterns indicating natural or artificial origins for various populations of cosmic visitors. The development of rapid response capabilities for intercepting and studying future interstellar visitors represents one of the most important priorities for space exploration and planetary science. The ability to collect samples and conduct close-range observations of such objects could provide definitive answers to questions that remain unresolved through distant observation alone. The integration of interstellar object research into broader programs of astrobiology and the search for extraterrestrial intelligence is creating new synergies between previously separate research areas. The recognition that evidence of cosmic life and intelligence might be found in our own solar system rather than through radio signals from distant stars is transforming SETI methodology and expanding the scope of astrobiological research. The public engagement and communication challenges surrounding interstellar objects reflect broader difficulties in communicating scientific uncertainty and the process of discovery to audiences accustomed to definitive answers and clear conclusions. The ongoing mystery of objects like 3I/Atlas requires science communicators to convey both the excitement of potential discovery and the importance of maintaining appropriate skepticism throughout the investigation process. The educational opportunities created by interstellar object research extend from professional training in new analytical techniques to public education about scientific methodology, cosmic environments, and humanity's place in the universe. The interdisciplinary nature of such research provides excellent examples of how scientific understanding advances through collaboration between diverse fields of expertise. As we reflect on the journey that began with the detection of Oumuamua in 2017 and continues with the ongoing study of 3Y/Atlas, we see a transformation in human understanding of our cosmic environment that may prove to be as significant as the Copernican revolution that displaced Earth from the center of the universe. We are discovering that our solar system is not an isolated island in empty space, but rather a dynamic environment that participates in galactic processes through regular exchanges of materials and possibly information with cosmic neighbors whose nature and intentions remain tantalizingly unclear. The implications of this transformation extend far beyond astronomy and space science to encompass every aspect of human knowledge and experience. We are being forced to expand our conception of what is possible in the universe, to develop new frameworks for understanding intelligence and technology on cosmic scales, and to prepare for potential contact scenarios that could fundamentally alter the trajectory of human civilization. Whether 3I/Atlas proves to be an ancient comet, a biological arc, an artificial probe, or something even more extraordinary, it has already succeeded in expanding human consciousness about our place in the cosmos and our potential connections to intelligence and life throughout the galaxy. The questions it raises about surveillance, communication, guidance, and contact will shape human development and exploration priorities for decades to come. The story of these cosmic visitors reminds us that the universe is far stranger and more wonderful than our current understanding suggests, filled with phenomena that exceed our imagination and possibilities that transcend our current knowledge. As we continue to explore and investigate these mysteries, we are not merely studying distant objects, but examining mirrors that reflect our own potential futures among the stars. In the gentle mathematics of orbital mechanics and the whispered chemistry of molecular emissions, in the precise trajectories that seem too perfect for coincidence, and the emission patterns that might encode the wisdom of ancient civilizations, we are receiving our first lessons in galactic citizenship from teachers whose identities remain hidden behind veils of cosmic distance and technological sophistication that we're only beginning to penetrate. As you drift into the peaceful embrace of sleep tonight, carried along by our planet's rotation through the cosmic dance that connects us to every star in the sky, remember that somewhere high above us, racing through the darkness at velocities that humble our fastest spacecraft, ancient messengers continue their eternal journeys between worlds. Whether they carry only the natural poetry of cosmic evolution or the intentional communications of civilizations whose names we have yet to learn, they remind us that we are part of something immeasurably vast and beautiful, something that connects every atom in our bodies to the nuclear furnaces of distant suns and possibly to the thoughts and dreams of beings whose existence we can only begin to imagine. The universe has sent us visitors, and we are finally advanced enough to notice their arrival. What they tell us about the cosmos, about intelligence, about life itself, and about our own future among the stars continues to unfold with each passing observation and each new piece of evidence. The conversation between Earth and the galaxy has begun, whether whispered through the behavior of mysterious objects or shouted through the obvious presence of artificial intelligence, and we are the first generation of humans privileged to participate in this cosmic dialogue. Tonight, as 3i/Atlas races toward its hidden encounter with our sun, as countless other objects move silently through the spaces between planets, as our radio telescopes listen for signals and our optical instruments search for anomalies, the greatest story ever told continues to write itself across the sky above us. We are no longer alone in wondering if we are alone, because the evidence has finally arrived to begin answering that eternal question carried across the impossible distances between stars by messengers whose origins and purposes continue to challenge everything we thought we knew about our place in this vast, mysterious, and undeniably inhabited universe. Sleep well, dear explorers, knowing that while you rest, the cosmos continues its ancient work of bringing intelligence together across the infinite expanses of space and time, weaving connections between worlds and species and civilizations in ways that we're only just beginning to understand. The age of cosmic solitude is ending, replaced by an era of galactic community whose true nature we will discover together, one mysterious visitor at a time, as we learn to read the messages written in the trajectories of wanderers from the spaces between the stars.